we started discussing in some detail RG flows between a UV fixed point and an IR fixed point. So I wrote again this general theory, which has, the metric, a dilaton, and the gauge field. I wrote down the ansatz that we are going to be using. It's a radial ansatz. The gauge field has only a time component that will let us introduce finite chemical potential, and the scalar is allowed to be a function of the radial direction. But why did I write this down? So when we were examining RG flows with relativistic symmetry, we have Minkowski metric here. We are not breaking any of the Lorentz symmetries or any translations. I wrote down a much simpler theory. I don't need the gauge field. And I also wrote down an ansatz for the metric. And again, the scalar is a function of the radial direction, right? So now we said that close to the IR fixed point, somehow our scalar should approach in this fashion. Phi IR is the value of the scalar field in the IR fixed point. Close to the IR fixed point, it has some conformal dimension delta IR. And the operator from the IR fixed point point of view, it should be such that its dimension should be greater than D, right? So it should be an irrelevant operator. That makes it an IR fixed point. So from this point of view, this term as R goes to 0 converges, right? This exponent is negative. And I need to set this constant of integration equal to 0. Otherwise, I'm not flowing to this IR fixed point. From the UV point of view, the operator needs to be relevant and stable. So we should satisfy the BF bound. And the UV conformal dimension should be smaller than D. So you see both of these terms converge as I take R to infinity, and the scalar field will take its UV fixed point value. Good, that's what I want to happen, right? But I still need to solve some equations. So why have I written these equations here? Well, the reason why I wrote these equations is because you can get the equations that this function U should satisfy and phi just from looking at these equations. So I can get this ansatz from that ansatz by setting, I don't know, I have to set, what do I have to set? F of R is square root of U, and G of R is 1 over square root of U. Okay? Now you see, okay, P is 0 here. I have no gauge field. So the Maxwell's equations will be satisfied trivially, but now you see that I have how many functions? 2 functions, U and phi, to satisfy 3 non-trivial equations. Okay, so some kind of miracle should happen, and the miracle does happen. So if you plug in these constraints into these equations, you can get some equations for U. So the first equation that you get for U is that U primed is 2RV divided by D minus 1, and then 2D D minus 1 minus R squared phi prime squared times phi prime squared. And you get another algebraic equation for U, which is 2V divided by minus 2D D minus 1 plus R squared phi prime squared. And you also get an equation for phi, which is a simple one, square root of U divided by R to the D minus 3 times R to the D plus 1, U to the 1/2, phi primed minus V is 0. Now, what you can check is that you can get this equation by taking a derivative of that equation and using the equation of motion for phi. Okay, so you can actually drop this equation, right? So this is a much more constraining equation. It doesn't have any derivatives for u. So this is telling you that if you take then u and plug it in here, you will just have to solve a single equation for phi. Okay? You will have a final equation which only depends on phi. So if I call this equation 1, equation 2, equation 3, what I'm telling you is to drop equation 1, because you would satisfy it anyway if you satisfy equation 2, and then plug the solution that you get for u from equation 2 in 3. Okay, so the whole system boils down, yes? Where exactly? Where exactly? Do you mean here? An overall factor. Well, you see, if I set phi prime equals 0 and I go exactly at the fixed point, I will get the correct expression for the radius of ADS, right, from this. So I would get that 1 over L squared would be minus V of phi naught, the fixed point, divided by D minus 1. So this factor of 2 cancels out. But you would have to use 3. Yes, it's not automatic. You have to use the equations of motion of the matter fields. This is equivalent, in fact, you know, if you have r mu nu minus 1/2 g mu nu r is equal to some stress tensor, to show that this is, this has to be divergence free, right? So what you're actually checking by taking a derivative of this and getting that is just the Bianchi identities at the end of the day. So you definitely have to use the equations of motion of the matter fields. So you would have to use that, you know, the stress tensor is divergence free. Yes.
One of them is not independent of the other. There is some symmetry in the action.
There is no miracle. I mean, the whole miracle is this. Einstein's tensor is divergence free by construction. That's what gives you all these miracles.
So, but then here, are you saying one of them is like a Bianchi identity and not an equation of motion?
Well, there is another, okay, if I look at these equations, and I just look at Einstein's equations, all the components of that thing, there is another equation which I have not written down, which is a second derivative of f, I think. Mm-hmm. I have completely dropped that. And the story goes on. I mean, I'm getting this constraint because I have basically set g equals 1. So if I look at the equation of motion, not g equals 1, I mean, I have fixed the relation between g and f. So as long as you make a reasonable ansatz, which is allowed by coordinate invariance. So, I mean, the most general thing that someone would write is this. Some function, I want Lorentz symmetry, right? So that has to be here. That's, and some other function, well, not these functions, not these f and g, times this. This cannot go wrong. But I can use diffeomorphism invariance in R and set, you know, this function to be R squared.
Yeah, okay. So it's just a good choice of ansatz that's helping this.
Yes, there was a lot of trial and error the previous days. Okay. So yes, and this is why I'm showing you this example. It just boils down to some equation for a scalar field. So, okay, so I have a second order equation for this function phi, right? And now I want to tell you how these constants are fixed. So the UV deformation is fixed by you. I don't know, fix it to be 3.5, something, okay? And then you have a second order equation in phi, and you would need to fix two constants of integration to find a unique solution, right? So this is one constant of integration that you fix, and this is the second constant of integration that you fix. Okay, so this is telling you that the UV value and the IR deformation parameter are fixed by the UV deformation parameter. Okay, so the UV deformation parameter sets the scale for every other constant of integration in the problem. Are we clear with that? And after explaining you this, well, I said I would do it yesterday. I didn't do it yesterday because I haven't explained this. I will send a Mathematica file to see precisely how you do this integration. I mean, it's called double-sided shooting method, just to get an idea of how you do things. Okay? Good. So this is for the relativistic RG flows. Now, what else do I want to tell you? Right. Now we want to go at finite chemical potential. Basically, look at this kind of theory, a more complicated one. Well, if I have a finite chemical potential, there is no further simplification you can make in your answers, right? So you have some preferred direction in your Minkowski spacetime on the boundary. That's the time component. I mean, you cannot write something simpler than this. But what are the requirements on this potential? So now what I have in mind is to flow from ADS on the boundary, on the conformal boundary, which would be the UV theory, to what we called yesterday hyperscaling violating geometries in the infrared. Yes. Please do.
So this is probably just nomenclature, but why are you calling it an RG flow? I mean, I just don't see precisely what is flowing into what. It seems to me that you're solving some equation of motion,
Yes.
And it has two different, basically asymptotic regimes, one close to the... Why is it called an RG flow then?
I will tell you.
Oh, okay.
Not now. Okay? Yes. So yes, there is this nice geometry which has two fixed points. Nice. If you look at it, so what? You know what? I will tell you now. Okay? You changed my plan. Okay. Then we will go back to these other flows. Okay? But maybe that's more interesting. What is the title? The title I want to give to this is Imprint of RG Flows on Linear Response. Okay? So RG flows and linear response. Okay, so you have this geometry, and you're sitting on the boundary, and you say, okay, how can I see that there is this RG flow, and what does it even mean from the boundary point of view? What do I want to say now? Before I do that, I want to study basically the two-point function of some operator, right, on the theory which has been deformed. And I want to see what happens with retarded Green's function of that operator as I'm taking, frequency and wave numbers to be much smaller than the UV deformation parameter, and frequencies and whatever to be much larger than the UV deformation parameter. And before I do that, I want to convince you about something. Okay, so let's say that you have some Hamiltonian in your problem. You can be at finite temperature. Finite temperature is not a bad thing. And that you are deforming your theory by some time-dependent Hamiltonian. Okay? So then you have a Hamiltonian which depends explicitly on time. Okay. Now, I want to say that this delta H, I imagine that I am in the Schrödinger picture, right? So I'm integrating over all the spatial directions. There is some operator x, O of x, and I have some perturbative deformation parameter, which depends on time and x. So all the time dependence in this delta H of t comes from this explicit dependence of the deformation parameter. Now, what do I want to show you? I want to ask the rate at which the system absorbs energy. Okay? So the expectation value of energy would be the trace of, I don't know, your density matrix, rho of t, times the Hamiltonian. Okay? Now, if I think that this h of t is something perturbed, I will have a trace of rho of t times h naught plus delta h of t. Now, what is the rate? For the rate, I would have to take a derivative of this thing, right? So the rate is dw dt, and then I would get two terms. I would have a derivative of the density, with respect to time, of the density matrix times this h of t, plus a derivative with respect to the explicit dependence of this delta ht with respect to time. Okay. Now, this first term is 0. That's trivially 0. Why? Well, because the rho dt is proportional to the commutator of rho with h. Okay, so if you just use the cyclic property of the trace, you can show that this is actually equal to 0. So if I go back to what this delta h is, and I use the fact that the trace of rho of t times O of x is just a one-point function of O of x, then you can show that the derivative of w with t is the spatial integral of the perturbative vev times the source. Okay? Now, what do we know about the response? We know that the perturbation of the response is given by the integral of the retarded Green's function. Let me put t x here, t minus t primed, x minus x primed, of delta x, t primed, x primed. Okay? Now, if I integrate the rate over time, and I use the Fourier transforms, I can show that the system absorbs a total energy, which is minus 1 over 2 pi d. I'm introducing the Fourier transforms now, integral over omega and over all wave numbers. Times the complex conjugate of the Fourier transform of the source times delta h omega comma k times omega times the imaginary part of the Green's function. Okay, so what this tells you is that the imaginary part of the Green's function gives the rate at which the system absorbs energy. So from the experimentalist point of view, this is where the good stuff is hiding, right? In the imaginary part of the Green's function. It tells you how the system responds against a time-dependent external source. Now, what do I want to tell you about the flows? Yes? In here? Exactly. There is actually two terms. I haven't done this in a long time. Well, okay. Right. Yeah, 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 yeah. Okay, so what is important now with these RG flows? So if I look at a scalar operator, basically I would be solving the Klein-Gordon equation, let's say, in this RG flow. Then you can, there is an argument which I don't want to run right now, which tells you that if you look at the imaginary part of the retarded Green's function, and you do this, then for small values of lambda, this goes like the imaginary part of the Green's function from the IR point of view of lambda omega and lambda k. So you could be getting the IR scaling, right? And for large values of lambda, you could be getting the UV scaling. So there is a crossover as I'm changing the scales of frequencies and wave vectors from the IR to the UV. And this argument is based on the fact that you have these two endpoints in your geometry. I mean, you can actually show it, right? You just look at the equation, you take various scaling limits, and you see that the IR geometry dominates at low energies, dominates the perturbation. You know, at the end of the day, I mean, this is why people are just so obsessed with the IR fixed points, with the horizons. If all you care about is long wavelengths and small frequencies, this is all that matters in the end. This is called a matching argument. You match basically UV and IR behaviors. Okay. Okay, there is a time derivative here that I missed. Okay, good. So let's now talk about the more general RG flows that would take you to these hyperscaling violating geometries. Okay. So let's talk about G flows. at finite nu. Okay, so the RG flow that I want to end up with now starts from some ADS fixed point in the UV and terminates to some hyperscaling violating geometry in the IR. Right, so for such a flow to happen, there is certain requirements on this potential V, right? So from the UV point of view, so let's call it UV requirements, there has to be some extremum of the potential. Let's say that the extremum is at phi equals 0. I mean, it can be some other number. The value of the potential at this extremum should be negative, so that you will actually get an ADS fixed point. You want phi to be relevant, so the mass of the operator, mass squared, should be negative, and the mass squared is the second derivative of the potential. And this function z should go to something constant. Let's say that z of 0 is just 1. It can be other numbers, but you can always scale things away and just reduce it to something like this. Now for the hyperscaling violating geometry, it is that z which is not here. Thanks, Carlos. That makes a difference. Well, now it isn't. Good. Right. So in order to have some hyperscaling violating fixed point, you need that for phi large, you basically want the behavior for the potential and the function z to be as we discussed yesterday. You know, some exponential behavior. Some constant z naught e to the alpha halves phi. Now, I want to give you a specific example of such a v and such a z, which comes from this dimensional reduction that we discussed, you know, from the 11-dimensional supergravity point of view. I mean, the dimensional reduction that I showed you was only keeping what? The metric, the 4-dimensional metric, and the gauge field. You can actually retain an extra scalar, which comes from a combination of the 4-form field and the metric. It is a very tricky combination to guess, but you can guess it, and you can retain it. And at the end of the day, you get a theory like this, with some fixed v and some fixed z. And the precise form of v is minus 24 hyperbolic cosine of phi over root 3. And z is 4 over hyperbolic cosine cubed of phi over root 3 times 1 plus 3 hyperbolic tangent squared phi on root 3. Okay? So indeed, you can check, I mean, if you ignore z, you can check that v gives you ADS space with an operator that has a UV dimension 2, which is a good thing. It's relevant. And for large phi, v of phi goes like minus 12 e to the phi over root 3. And z of phi goes like 8 times e to the square root 3 times phi. So this is giving me that beta is minus 2 over root 3, and alpha is minus 2 root 3. There is a minus sign here. Now, from this alpha and beta, you can use the formula we wrote yesterday, and you will get some hyperscaling violating geometry, which has theta is 1 and z equals 3. Okay? So indeed, I mean, from 11-dimensional supergravity, you can get such a solution that flows from ADS to these hyperscaling violating things. And now I want to, yes? It is like this, yes. It is a runaway potential. If you were in flat space, yes. However, with ADS asymptotics, you can have a little bit of negative m squared. That's okay, it doesn't hurt. So it is enough. I think I erased it. So if it was too negative, that could give you, that would violate the BF, I mean the mass for the scalar would violate the BF bound, which is, I don't know, dimension minus d. Dimension is d minus 2 over 2. If it was that negative, you are in trouble, yes. If I was not deforming my theory, everything would be nice and stable. There would be no dynamical instability, and there is no dynamical instability. However, I am deforming my theory, and that's exactly what I want to happen. I want it to run away and go here, so that I will have the hyperscaling violating thing. Okay, good. Okay, so now I want to see what it takes to basically construct such a domain wall between, I mean, an RG flow solution between ADS and the hyperscaling violating geometries. So you see, we used that ansatz to find the IR fixed point, but I'm using exactly the same ansatz to find the whole flow. Okay, so that's a big set of solutions. So somehow I need, again, to count constants of integration and show you that I have exactly enough that I will get a unique solution if I fix the chemical potential and the deformation for the scalar operator. So close to the conformal boundary, which is R goes to infinity, let me look at this function g of R. So g has only a single derivative, okay? So I'm expecting to get exactly one constant of integration. You can probably guess this constant of integration if you just, scale time. Scale time, or you can scale f and g at the same time. So there will be this constant, g naught, times some expansion for the function g. Okay, but the constant of integration is just a number. Now, f also satisfies the first order equation. Now, the constant of integration that comes from g will also multiply f. Okay? And the constant of integration that comes from f is going to basically give you this constant of integration that we were discussing from the metric perturbations that come with a power of 1 over r to the d. Okay, so that's another number, which I'm calling m. Now, for the gauge field, P of r, there will be, again, g naught will appear there. You see time scalings also affect the gauge field, I will have a constant of integration mu, which will be the potential, and then a second one, which will fix the charge density of the solution. And phi, as usual, it will have the source term. It is a second order equation. It will give me some source, d minus delta uv, plus terms that I can find by solving the equations of motion, and then another constant that will fix the vev. Okay? Good. So what am I expected to fix from the boundary point of view? What does my physics want to fix? So G naught, I mean, if I go strictly to R goes to infinity, I will find some, and I keep G naught to be not 1. I will just find Minkowski space with some different speed of light. Okay? So I want the speed of light to be 1. So yes, G naught is gone. I have fixed it because I'm fixing my speed of light from the boundary point of view. What else am I expected to fix? I am expected to fix the chemical potential mu, right? So that's part of my deformations. I should be under control of this parameter. What else do I fix? I'm also fixing the scalar deformation. Okay? So this leaves me with how many undetermined constants of integration? There is this. Well, we were expecting to not be able to fix this just by looking at the boundary. We said this is part of the response of the thing. So somehow the horizon has to play a role, or the IR geometry. The charge density is not supposed to be fixed by us. And then there is a third constant, this 5e. Okay, so these are not fixed just by fixing deformations, chemical potentials, and stuff like that. Okay. Now I need to look at the solution from the infrared point of view. And this is where these static modes that we were discussing yesterday are going to play a role. Okay? The static modes around this IR fixed point. So close to the IR fixed point, again, I'm going to use a slightly different coordinate, radial coordinate, so that the exponents will not look horrible. I'm using the rho coordinate to write down the solution. So we said that f of rho will be some function, some number f naught times rho to the z minus 1 plus theta over d minus 1 times 1 plus some static modes. And the static mode that I want to use in this case is this delta plus mode, which is a positive number. Now G will be some number G naught times rho z to the minus 1 plus z minus theta over d minus 1 times 1 sorry, this is f plus a g c phi times rho to the delta plus whatever. And p of rho will be some number p naught rho to the d minus 1 plus z minus theta times 1 plus a c p rho to the delta plus and phi. So there is a number which is fixed in terms of z, d, and theta times log rho over rho naught plus A C phi rho to the delta plus whatever. Okay, so there is now 3 constants from the UV point of view, but as we said yesterday, there is 2 scales, right? So 2 constants of integration, which are just scales. One scale is P naught, and another scale is rho naught, which are free parameters for the time being. And there is a third parameter, which comes with an irrelevant operator, which had exponent delta plus when we were looking at these static modes. So this is another 3 constants. Okay, so in total, there is 6 constants that need to be fixed. Now, if you count derivatives here, in this system of equations, G has 1 derivative, F has 1 derivative, there is 2 derivatives for phi, and 2 derivatives for P. In total, I need exactly 6 constants of integration to find a unique solution to this problem. So as soon as I fix my UV deformation parameters and this G naught, I'm guaranteed, well, guaranteed. I can only have a unique solution to this problem, right? And that's precisely this RG flow that I am after. Okay, so this counting works. So the point is that if I had not found this extra irrelevant mode, if that mode was not there from the IR point of view, there would be no chance that you could flow to this fixed point. Okay, so this extra operator plays an important role.
So you have 6 derivatives?
Yes.
3 interaction constants there, 3 here.
Mm-hmm.
Okay, that's the shooting method will work.
Yes.
And then can you tell again why that? Okay, because if I don't have A.
Okay, so the 2 constants from the IR point of view came just as constant integration of the background. They are just some scales which were not fixed just by looking at it. If this extra irrelevant mode did not exist, which comes by looking at perturbations around this fixed point, then there would be no chance of connecting this with a UV. It would be, I think, you would need more numbers than you have at your disposal. Exactly. It could be an overdetermined problem. It could happen by accident, but you would not be guaranteed that the solution would exist. Yeah. Or it could be an RG unstable fixed point, right? It could be separating 2 other fixed points. There could be a phase transition between these other 2 fixed points, and this fixed point could be sitting at the middle. And when you would set the relevant operator equal to 0, you would just have exactly one flow. Yes? So which exponent? Here? The first term is just 1. That's the background. D minus, yes, D minus 1 plus Z minus D. Say it again? Oh, sorry. That's not D. Thanks for asking. I read it wrong. That's theta here. Thanks. Thanks for asking. Yes, you're paying attention. Okay, so this would be a zero, well, just an RG flow at exactly 0 temperature, right? Good. Now, I want to discuss finite temperature. Okay? So the story I want to tell, I mean, where things, well, I will tell you also other things in as we get there, but I want to tell you that I can just hit this thing up, and when I am at very small temperatures, I will know exactly how the finite temperature horizon will be behaving just because I have this analytic solution. Why do I even care? Maybe I will tell you tomorrow. Okay, so let's talk about a few things about finite temperature. Is there any other questions? Yes, good.
Because we establish some behavior at the boundary, right?
You mean here?
Yes. But how we? I was thinking that we flux between one theory and the other, right?
That's the goal. Yes.
This that we did is a flux.
Oh, yeah. So what we established is that there will be a solution that precisely does that, just by counting constants of integration. That the system of equations that I have over there will have a solution that will represent an RG flow.
Okay.
Okay, just by, I mean, if this counting did not work, then it would be exactly what we were discussing with Carlos, that you would be in trouble, that there wouldn't be a flow.
All right. Okay.
Right. So finding the solution in closed form, it might be done. I think there might be analytic solutions that actually do this, but I wanted to show you, what. Okay, so what? If you have it, what does it mean?
Okay. Thank you. Thank you.
The other two are, scales that came with the solution. There was a scale P naught, and another, this scale rho naught. So you would basically have to fix this scale. And that's part of what I wanted to say yesterday, that this scale is fixed by UV data. You cannot just take this solution and pretend that you have forgotten about the UV theory and that everything is independent of that.
Mm-hmm. Got it.
Good.
You mentioned that this example is from M theory. So
that I had over here?
Yeah.
Yes. Okay.
So phi is the dilaton of M theory. That is the signature here of M theory.
Phi is basically coming from the four-form flux. It also appears in the metric. I mean, you would have to do a nonlinear identification of a field. So I wouldn't call it a dilaton. It's also a pseudoscalar. It's not a scalar.
Okay.
So I wouldn't. People want to call these dilatons. It's not a dilaton. It's a scalar field.
Okay. Thank you.
Okay, so it's good that Jan yesterday talked about quite a few things about finite temperature. That makes my life simpler today. So, okay. So what do I want to achieve with finite temperature? So right. So what I want basically is, from the bulk point of view, is you see, we had this UV expansion close to the boundary, right? And I fixed mu, I fixed the scalar deformation, and I fixed G naught. I want to consider my theory with these things fixed, right? But bring it at finite temperature. Okay, so I want to add temperature to my parameters. And so how am I going to achieve this? So basically you want to construct a geometry where you have your UV boundary. And here is where you fix the chemical potential, scalar deformations and everything. Those things you keep fixed. But now, instead of an IR fixed point, you want to have something simpler. You want to have an event horizon, a planar event horizon in the bulk, okay? So if I make, the same assumptions about not breaking rotations or translations or any of the Euclidean symmetries from the dual field theory point of view, the ansatz that I would use for such a theory is exactly the same. Nothing changes about the ansatz. Okay, so all the temperature that could break would be probably Lorentz invariance, but Lorentz invariance is already broken here by the finite chemical potential. So as far as the symmetry of the solution goes, it's an identical thing. I'm not going to change anything. What is going to change is how things are going to look like in the bulk. So a regular event horizon would be at some point, in the radial coordinate r equals r naught, where in this coordinate system, f has a 0. The derivative of f at this point is not 0, and g is also a non-zero function. Now, if you manage to achieve that, then the temperature of this, the Hawking temperature of this black hole horizon would be the surface gravity divided by 2 pi. And maybe you can check that the surface gravity in this case is r naught squared f prime at r naught divided by 2. So the temperature would give you, r naught squared f primed over 4 pi. Good. Now, the surface area density of the horizon, and I'm saying density because that's a planar horizon, right? So you can define area densities there. The area density of the horizon would give you the entropy density. So then you would have entropy density, which would be S. So I'm setting, you see, if you look at that, I'm setting G is 1 over 16 pi. The gravitational constant is 1 over 60 pi. And that would give me an expression for the entropy density, which is 4 pi times the square root of the horizon metric. And in this coordinate system, it has a simple expression in terms of the value r naught. Now, right. So if I now go to Euclidean time, I don't want to repeat too many things that you have seen before. Then I can expand the function f like this, and what you will get in the end from a Taylor expansion, just by keeping the leading terms in r minus r, in r minus r naught, is that you can approximate f of r by 4 pi t over r naught squared times r minus r naught, plus corrections. And the function g of r would be this constant g naught plus higher analytic terms. As Jan discussed, if you look at regularity of this metric close to the horizon, you will conclude that if you do a Euclidean, if you go to Euclidean time, then you will have correctly identified the period of the thermal circle with 1 over the temperature. That would give you a regular geometry. Right, so you can make this metric in Euclidean time look something like this. So ds squared is basically like the origin of two-dimensional flat space in polar coordinates, right? So you can bring it into this form. 1 over pi t, 2 pi t squared, rho squared d tau squared, plus d rho squared, plus the geometry of the horizon, which is something regular. So at exactly rho equals 0, corresponds to r equals r naught. You have these polar coordinates, but what I want to discuss is now the behavior of the gauge field. Okay, so if you go to Euclidean time, then the gauge field close to the horizon would go like some function of the radius times d tau. Okay? Now, d tau, if you look at polar coordinates, is not a regular one form. Okay? If you are looking at radius and phi, d phi is not regular at the origin. It's not defined. What is defined, if I go to rho and tau, what is well behaved is rho squared d tau. That's the only regular thing that you can have close to the origin. And whatever can have higher powers of rho. But this is the least power of rho you need to have in order for the gauge field to behave regularly at the horizon. So if I go back to my r coordinates, you know, rho is basically like the square root of r minus r naught, then you find that to have a regular gauge field close to the horizon, your gauge field has to go like this. Okay, it has to vanish at the horizon. And in these r coordinates, where there is a function that vanishes here and the function that vanishes there, then it better be that the gauge field goes to 0 like this, close to the horizon. Okay, that would be a regular behavior. Okay, what else do I want to tell you?
So suppose that I don't care about the gauge field, but the field strength, right?
Okay.
What will I observe if I don't go like this? What will be the problem? If you
Let's say that you have a charged scalar,
yeah.
right? And the gauge field couples to the charged scalar. You will see things just blowing up. You will have A there in the equations of motion of the charged scalars, and things would be super singular.
Good.
You can say, okay, then I can, you know, multiply the scalar by e to the it, whatever, but then t is not a regular coordinate on the horizon.
Just as a comment, the R0 is like a gauge transformation, right? So the bit
This
R0
thing.
dt is
Oh,
like
yes,
a gauge
you know.
transformation. Yeah.
This is always a solution of the equations of motion.
Right.
It has 0
Right.
field strength.
Right.
But I have to combine this solution with anything else to achieve this.
Okay, very good.
And this is what fixes the chemical potential at infinity, right? So you can, I mean, there was this discussion. I can set the chemical potential to 0. Yes, okay, but you have to be very careful at the horizon. Okay. Good. Okay, so let's, well, I want to do a little bit of counting of parameters now that we still have things fresh. So again, I would have to solve these equations, right? From the UV point of view, nothing changes. There is still 3 constants of integration. Somehow, I need to discover another 3 constants from the horizon in order, again, to find a unique solution to this. So let me tell you how these functions are behaving. So as we said, G goes like G naught. So G satisfies a first-order equation, right? G naught plus, I don't know, some expansion. Now, this G naught is one constant of integration. Another constant of integration comes from phi. So phi will take some fixed value on the horizon, some finite value, plus some expansion which is determined by the equations of motion. You will say, okay, phi satisfies the second order equation, so where is the second Where is the second constant of integration? Well, the second constant of integration, let me call it, I don't know, phi 2, goes like a log. So that could be singular. So you need to set this constant of integration to 0. That's a very useful mode if you're doing hydrodynamics, I mean, from the static point of view, but we are not doing hydrodynamics yet. It's just statics, right? So you set that equal to 0. Okay? So that's the second constant. Now, the gauge field, I mean, P parameterizes the gauge field. I just agreed with myself that P should be going to 0. And it turns out that this P naught here, this constant, is another constant of integration, right? So that's the third one. Now, F should go to 0. And this F1 is fixed by everything else. Okay, it's not another constant. I already have these three constants. And there is many different ways now to phrase the fourth one, which will be the free parameter which sets the temperature. So the free parameter that I have, which actually sets the temperature of the system, you can think of it either as R0. Well, that would be really setting the entropy of the system. Or you can say, yeah, okay, I don't know where the horizon is. I'm going to say that this is a free constant. And this constant would set actually the temperature from here. And you could be looking for R0. Okay, so in total, you have these three constants that give you a solution and an extra parameter which gives you the free temperature. Okay, and as you vary this temperature and you take it to 0, what you want to say is that these black hole solutions will actually converge in a non-trivial way and in a singular way to these IR fixed points. Okay, it is basically changing from this analytic expansion to some non-analytic series, which happens at exactly 0 temperature. What else do I want to tell you about the finite temperature stuff? Okay, so let's say that you have this. Exactly, yes. Well, I mean, these powers that we had, yes, exactly. So these powers that we had in these functions at the IR fixed point, they are in general non-integers. They are so. Exactly. We will see exactly how this jump is happening. We are going to use this mode that heats up the solution in the IR, and we will see how small black holes look like. Okay, so. Right, so let's say that you have such a solution. Then you might wonder about the Gibbs free energy. So the Gibbs free energy would be minus T. I have set Boltzmann's constant equals to 1, of course, times the log of the partition function. And if I am at the strictly classical limit, then I know that the partition function would simply be the exponential of the Euclidean action. And so the Gibbs free energy would be temperature times the value of the regularized Euclidean action. Okay? Now what is non-trivial is that this free energy that you evaluate from the on-cell action is actually equal to the energy of the system minus Ts minus mu rho. You can say, yes, of course, this is what it has to be. But to show this, I mean, if you think about it, what is this energy? This energy is basically the stress tensor, right? That's a boundary quantity. Mu rho, that's again another boundary quantity. I mean, I'm reading off the charge density from the boundary point of view. Ts is something that comes from the horizon. You can actually show this, right? It is what should happen. But in order to show this, you basically need to show that the bulk action, which is this, is basically a total derivative on shell. And so if you write it as a total derivative, then it's obvious that you will pick up contributions from either the boundary, the horizon, and these contributions work out precisely to give you this expression, okay? Okay. What do I want to tell you now? I think I'm going to skip a lot of things because we will definitely run out of time. But I will give these notes to be uploaded. You can see things that will not be said here. Now I want to talk to you about the low temperature limit of these hyperscaling violating black hole geometries. Yes? Exactly, right. So that could be the free energy of the boundary CFT. Right, okay. So now let's see how you can heat up this IR fixed point. Well, the RG flow, basically. Okay. So let me go back. Let me write again. I shouldn't have erased this. How the near IR fixed point geometry looks like when you have the domain wall. I mean the RG flow solution. So now I'm imagining I have this RG flow, and I'm just focusing at the region very close to the horizon, right? So I should see all these modes. I should see the irrelevant mode, which is this delta plus whatever, and G of rho should be G naught times another power. One plus A CG rho to the delta plus P of rho P naught rho D minus 1 plus Z minus theta and 1 plus A CP rho to the delta plus, and then phi of rho, which is some number times the log of rho over rho naught plus C phi rho to the delta plus. Okay, so good. So this is the, strictly speaking, the zero temperature solution, the RG flow, right? Now, we said that if I looked at static modes, there is an extra mode, let me write it in yellow, which modifies, there is two modes in fact. The first mode only modifies this function f, so it will give me some constant times rho to the delta t plus something. And the second mode only modifies the function p, where the function p is basically coming from the gauge field. Let me call it Cp times rho to the delta t. Okay, so let me add this tiny small mode to my whatever RG flow that I have. Now, let me remind you what this delta t is. So delta t was theta plus 1 minus z minus d, and that's a negative number. Okay? So if it is a negative number, as I'm moving far away from my solution, it fades away, right? So it doesn't affect really the geometry far away from the IR fixed point. It's just a tiny small perturbation. However, as I'm going near the fixed point at rho equals 0, and since this exponent is small, this becomes stronger and stronger, okay? In fact, it becomes as strong as the background. And this is why it was important to stress that adding this is actually a solution to the full problem. It's not just a perturbation. When you have a perturbation which becomes as big as your background, it's not a perturbation anymore. So this is a full solution, right? So let's see what we can do with it. So as long as I'm staying in the small rho region, I can choose these constants of integration in the following way. So I can choose Cf to be equal to some number rho plus to the power minus delta t. And I can choose Cp to be equal to minus rho plus to the power minus delta t. Rho plus is just some number. Okay? So as long as I choose them in this way, this expansion is telling you that we obtain a finite temperature horizon at rho equals rho plus. Okay? So as rho becomes small, you can start forgetting about this, and then at exactly rho equals rho plus, this term is going to cancel out the 1, and f will have a 0. And we said that at the same point, if you need to have a finite temperature horizon, this p also has to go to 0. So the second constant of integration is precisely chosen so that you get another 0. Okay? Good. So what can we do with that? So we have this parameter rho plus, and now I can use the form of f to find the temperature in terms of this rho plus. So temperature was r plus squared times the derivative with respect to r in the r coordinates, not in the rho coordinates. There is a small change of coordinates here, or variables. And you can express the temperature in the end as this constant f naught over 4 pi times some number, d minus 1, d plus z minus 1 minus theta over d minus 1 minus theta times rho plus to the power z. Okay? What can I do with that? So the other thing that I can do with this, so now we have a relation between rho plus and temperature. So what I can do by using this equation is that, I know that the entropy density is 4 pi times r plus to the power d minus 1. And so I can use this, I also know the relation between r and rho, which I have erased. R is rho to the 1 minus theta over d minus 1. And similarly for r plus and rho plus, this is what I call r plus here. And so I can use this to get an expression for the entropy density in terms of temperature. So, and if you do that, you will find that the entropy density scales like T to the d minus 1 minus theta over Z. That's the first thing you can do about this IR fixed point. The second thing that you can do is that you can find actually the value of the scalar field on the horizon as a function of temperature. So the scalar field at rho plus, you can show that it scales like this number will, I think, 1 over Z times square root d minus 1 minus theta, and then d minus 1, Z minus 1 minus theta, divided by d minus 1. And then you have a log of temperature. Okay? So that's the value of the scalar on the horizon as a function of temperature. I totally sympathize if you're saying, yes, okay, the entropy is an interesting quantity as a function of temperature. Who would ever care about the value of some scalar on a black hole horizon? Okay? So I hope that tomorrow's lecture will tell you why we should care about this. So it is going to basically fix transport coefficients from the dual field theory point of view. Okay, I think I want to stop here. And I think you want to stop here.
Any question?
So maybe this is a sort of a question of the meaning of what we're doing. So I'm not sure exactly how we should consider all these constructions. So so when we talk about having an RG flow, so are we basically saying that there is this on the ADS boundary of this theory lives a CFT, which is a UV fixed point, and then we have this solution is the bulk that connects this CFT on the boundary with some I would say some other CFT that lives on a horizon or the r equal to 0 brane. And is that a different CFT? Like it's a completely different CFT, or is just
It's a different fixed point.
Okay, it's a different fixed point, which means I'm somewhat renormalizing the.
And you just keep all the low energy degrees of freedom. All that matters about that fixed point.
Okay.
You throw, so you get this other fixed point which comes with its own irrelevant operators, stuff that will affect things at high energies. You forget about all that.
Okay, so dumb question, but I have to do this. Is there any explicit example in which this is, in which the CFT dual is known and one does some CFT renormalization and obtains the theory that I obtain on the...
In supersymmetric examples, yes. And there has been precision tests about this.
Very cool.
It is, yes. I hope you find it cool. Carlos knows a lot about this.
So just continuing that question, so we have a UV CFT, and we have a geometry corresponding to that, which is dual.
Mm-hmm.
Then and then there is another geometry, another solution of this set of equations, which is dual to some IR CFT.
Exactly.
That's and so the flow. And somehow what we've done is found a flow in the geometries also, which corresponds exactly to the RG flow from UV CFT to IR CFT.
Exactly.
That's the big picture.
That's what's happening.
Perfect. Thank you.
Good.
One more. So is it known some field theory that the entropy scales like that.
Um,
So maybe it's too much to ask for a Lagrangian, but
I believe there is experimental systems which seem to scale like that with a non-zero theta,
good, good,
which involve electrons. I mean, it's an experimental fact.
good. Perfect. Yeah.
Sure.
More questions? Okay, so if not, let's thank Aristos again and let's reconvene after lunch.
Thank you.